So this is the review video for the Unit 3 exam. And Unit 3, remember, covers work and energy, like it says up here. Alright, the first review question on here says, how do you calculate velocity? And this is from Unit 1. Remember that velocity is distance divided by time. And we know from Unit 2 that gravity is an acceleration, and gravity has a value of 9.8 meters per second squared. In question 3, it says you're given a mass, how do you calculate out the weight? The equation for this, remember, is that weight is equal to mass times gravity. The mass has to be in kilograms, and the gravity, just like before, is in meters per second squared, which makes the unit for weight newtons, which is a capital N. Okay, also from Unit 2, it says you are given a mass and acceleration. How do you calculate out the force? Keep in mind here that force is mass times acceleration, and the unit for force is newtons, just like the unit for weight was newtons. And the unit for mass is kilograms again, and the unit for acceleration has to be meters per second squared. Alright, the next set on this review is this table. And in this table, it's making sure that you know all the abbreviations that are in the formulas, as well as what unit you need to have for those formulas and the equation. So the first variable here is mass. Remember, mass, the abbreviation is at lowercase m, and the unit that we need it in most often is in kilograms. And if it's ever given to you in grams, you need to divide by 1,000. So getting from grams to kilograms requires dividing by 1,000. And there is no equation for mass, but mass is used in a lot of equations. Alright, the next variable on here, as you can see, is velocity. Remember that the abbreviation for velocity is a v, and the unit that velocity typically is measured in is meters per second. And the equation, which I know is kind of cut off on the right-hand column right now for velocity, is distance divided by time, like it was before, where the distance is in meters and the time is in seconds. Alright, remember that acceleration is a, and the acceleration due to gravity specifically is g, which is down below here. So that's g. And the unit for acceleration is always meters per second squared. And the units for gravity is also, because it's an acceleration, meters per second squared. Remember, the equation for acceleration is final velocity minus initial velocity all over time. Force is abbreviated as a capital F, and its unit is typically newtons or capital N. And remember from above that the equation for force is F equals m times a, or mass times acceleration. So weight was a lowercase w, but work is a capital W. The unit that we typically measure work in is joules or kilojoules. And we know the formula for work is W, or work, equals force times distance. Okay, the next one on your sheet there is power. Power is usually given by a capital P, and the unit for power is watt or kilowatt. And the equation for power is work divided by time. Okay, the next thing after power you can see is mechanical advantage. The abbreviation for mechanical advantage is a capital M and capital A together. There is no unit for mechanical advantage. Sometimes it is given as a percent, but usually there's no unit for mechanical advantage. And we know that the formula for mechanical advantage is either force output or the force out divided by the force in, or it's the distance out divided by the distance in. I'm sorry, it's that one is the other way around. It's the distance in divided by the distance out. So distance in divided by the distance out. So again, the unit or the formula for mechanical advantage, there's two formulas. One of them is the force output divided by the force input, or it's the distance in divided by the distance out. The next one is efficiency. So efficiency is usually abbreviated as a lowercase e. And its unit is almost always a percentage. And it's the work out divided by the work in times 100. So efficiency equals the work out divided by the work in times 100. And then you stick on that percent sign at the very end. Okay, there are two types of energy that we've studied in this unit. One of them is kinetic energy, and the other one is gravitational potential energy. Kinetic energy is KE, gravitational potential energy is just the initials GPE. Both of these are typically measured in joules. Sometimes you'll see them in kilojoules, but most often they're in joules. Remember that kinetic energy is the energy of motion, and so the equation for kinetic energy is 1/2 m times velocity squared, where m is the mass in kilograms and velocity is in meters per second. And then for gravitational potential energy, that's going to be mass in kilograms times gravity, which is 9.8, times the height in meters. So mgh is gravitational potential energy. And then down below here, height is h typically, and that's almost always measured. I lost internet connection for a second, so I'm not sure where I left off on the video here. I'm starting back over with kinetic energy. Kinetic energy is KE. It has a unit of joules or kilojoules, and the equation for kinetic energy is 1/2 mass times velocity squared. And remember, kinetic energy is the energy of motion. Gravitational potential energy is abbreviated as GPE. It also has units of joules or kilojoules. The equation for gravitational potential energy is mass times gravity times height. A lot of times it's written as mgh. Okay, so height is h, and it has the unit of meters. There is no equation that goes along with it. And the acceleration due to gravity, which I talked about before, was g, and it's measured in the unit meters per second square. And remember, it has a value of 9.8 meters per second squared. All right, we're off of the table now, and we're down to the bottom here where it says work. So right here, you should be on your review sheet. It says, when is work done? And then it says work is done only when the force applied. And the answer there is causes a change in the position of the object. So if there is no change in the position of the object, in other words, if the object stays stationary, there is no work done. The next section here has some definitions that you're responsible for. And the first definition that you need to know is work. And the definition for work is the energy transferred to or from an object via application of force along a distance. So work is a force applied over a distance. The next definition, power. Power is the work done per unit time. And that's just based on the equation, remember, where power is equal to work divided by time. All right, the next one on here is efficiency. And remember that efficiency is just a way of describing the amount of useful output a process or machine can generate as a percentage of the input required to make it go. The next thing here is machine. Remember we talked about simple machines and compound machines. A simple machine is just a device that changes the force or increases the motion to make work easier. Now, a compound machine is a machine that consists of two or more simple machines. The last definition here is mechanical advantage. Remember that mechanical advantage is the ratio of output to input force or input to output distance. All right, we just went through those definitions, and now let's just make sure that you have the units proper for the following things. The first one is work or energy, because they both have the same unit. Almost always it's going to be joules. Sometimes you'll see it as kilojoules. For efficiency, remember that we always report efficiency as a percentage, which is why we multiply by 100. Mechanical advantage has no unit associated with it. And then lastly on here is velocity, and this is from the last unit. Remember that velocity is almost always in meters per second. All right, the next question here is, can a machine be 100% efficient? Why or not? Why not? Remember that there is no machine that can be 100% efficient. And the reason is that some energy or work from machine is always lost due to friction or heat. There's always a little bit that lost from friction or heat. So the answer here again is no. And number 11, the three types of simple machines that we talked about, remember, were pulley, lever, and an inclined plane. Okay, and the next thing here, which is list 3 ways that machines are useful. And this has to be from your notes, not your opinion. The 3 things that we talked about as far as machines go being useful is, 1 is that they increase the speed of the work that you're doing. 2, they can change the direction of the force that you're inputting. And the last one is they can actually increase the force that you're inputting. All right, this next question is kind of a tricky one. It says, true or false, less work is done with the aid of a machine. And here the answer is false. And the reason is that the work is easier, but the exact same amount of work is done with or without the machine. And the next question, what can you tell me about the machine that has a mechanical advantage of over 1.0? We know there that it increases the speed or the distance. And then the next thing is asking you for some examples. Oops, I skipped over one of the questions, it looks like. The one that says, what can you tell me about a machine that has a mechanical advantage of over 1.0? So if you're over 1.0 mechanical advantage, that means that you're multiplying the force. So whatever force you're putting in, it's being multiplied. But then when it's less than 1.0, again, that means that you're still increasing the speed or distance. You're just not multiplying the force. And now let's look at number 16 here, some examples of these simple machines. So the example of a wedge might be like an axe. Remember that an axe, if you're looking on it straight on like this, is a wedge, and it pushes things, especially wood, apart. So it pushes part of the wood this way and part of the wood this way, and that's how that simple machine works. Even a nail or a doorstop is considered a wedge. As far as a ramp, a slide, a handicap ramp, or stairs are considered a ramp. And for a screw, corkscrews, or just a regular screw, that you would put into wood, would be considered a screw. And then a wheel and axle, this one is probably the easiest out of all of these. An example there would be like a steering wheel, a tire that's on an axle of a car, for example. All right, I know this picture is kind of hard to see here, but as far as pulley number 1, there is one support rope for it right there. For pulley number 2, there's actually 2, and they're right there. For pulley number 3, there are 3 support ropes. There's one there, and there's another one right next to it. And for pulley number 4, there are actually 4 support ropes. One on this edge, one on that edge, and then 2 on the inside there. So pulley 1 has 1 support rope, pulley 2 has 2 support ropes, pulley 3 has 3 support ropes, and finally pulley number 4 has 4 support ropes. In the next question it says, discuss the relationship between the length of the ramp or inclined plane and the mechanical advantage of the ramp. Now, if you remember from the PowerPoint that we did, when we have a ramp, the length of the ramp is the input distance, and the height of the ramp is the output distance. And so what this means is the longer the ramp that we have, the higher the mechanical advantage is going to be. Alright, so the next few things on here deal with energy. And the first one says define energy. So remember that energy is the ability to do work or cause change. And then 4 forms of energy. In the reading I had you do, there was mechanical, electrical, thermal, chemical, nuclear, kinetic, and potential, specifically gravitational potential. And then 21 here says explain the difference in potential energy and kinetic energy. Remember that potential energy is going to be energy that's either stored in the object or due to its position, like how high off the ground it is. Whereas kinetic energy is always the energy due to motion. So if an object is not moving at all, it will not have any kinetic energy. It looks like there was a question that got cut off here. It was number 22 on your review sheet. It says, state the law of conservation of energy. Remember that conservation of energy says that energy cannot be created nor destroyed. Instead, it will be transferred from one type or another, from one object to another. So again, energy cannot be created nor destroyed. Instead, it will be transformed from one type to another type, or from one object to another object. Okay, I'm going to try to do these problems here. The first one says calculate the power. the average power in kilowatts required to pull a car up a ramp if the amount of work is 250 kilojoules over a period of 45 seconds. For all of these problems, the way we want to handle it is write out and figure out the equation we're going to need. So in this case, we're looking for power. We're being given the work. We know the work is 250 kilojoules, and we're also given the time. The time is 45 seconds. And the equation for power that's above, as you can see, is that power equals work over time. So for this problem, we're going to take the work, which is 250 kilojoules, so again, because work or power equals work over time, we're going to take the 250 kilojoules and divide it by 45 seconds. And because we're taking kilojoules over seconds, that's going to give us a power answer in kilowatts instead of watts. So our answer here is going to be 5.56 kilowatts. And that's the answer for that problem there, 5.56 kilowatts. Okay, the next problem says calculate the mechanical advantage of a group of pulleys if an engine is raised 1.2 meters when 4.8 meters of rope is pulled through the pulleys. Okay, so this is going to be a mechanical advantage problem, and because we're given distances here, this is going to use the equation that uses distances for mechanical advantage instead of the one that uses forces. And normally the students have problems figuring out what the input and the output distances are. Well, here we had to pull 4.8 meters in order to lift the thing up 1.2 meters. So the 1.2 meters is the output distance, and the input distance is 4.8 meters, because that's how long we're pulling, or how much rope we've got to pull. So then our mechanical advantage is going to be 4.8 divided by 1.2 meters. And these are both meters, and since there's meters above meters, those will cross out, which tells us that our mechanical advantage is 4.0, or just 4. And remember, there's no unit on mechanical advantage, so we don't need a unit on this one. Alright, our next problem here says Billy Bob exerts a force of 58.2 newtons while pushing against a big wall for 15.2 seconds. How much work does Billy Bob accomplish? So for that problem, we know that we're looking for work, and we know work is force times distance. And it tells us in the problem that the force is 58.2 newtons. But because he's pushing a wall, it doesn't say anything about the wall moving, so we're assuming the wall did not move at all, which means it moved 0 meters. So the work is also 0. So it's kind of a tricky question because the answer there is 0 joules. And the thing to keep in mind is if the object that you're doing the work on doesn't move, there's no work involved. Alright, so in this next problem, it says the MA, or mechanical advantage of a lever, is 4.0. So that's this problem up here. How much force will you need to apply to lift a 600 Newton crate? So there we're going to need the mechanical advantage equation, which I'm going to do this whole problem so I have room down here in this area. So we know that the formula for the mechanical advantage when we're dealing with forces, which we know we're dealing with forces because of the capital N there on the 600 newtons, is going to be output force divided by input force. So force out divided by force in. And the force out, it tells us, is 600 newtons, because that's how much stuff we need to lift. So we're trying to figure out the force in. The other thing that we're given in this problem is we're actually given the mechanical advantage in this problem, which is 4. And remember, there's no unit on that, so we need to solve this, where 4 equals 600 over x, or force in. So again, the final equation that we're trying to solve here is 4 equals 600 over force in. You can do your math any way you want to here to solve for x or the force in. A lot of students have trouble solving for something when it's in the denominator. What I do math-wise is, if I have a fraction like this, I will swap these if need be. So in other words, we're going to end up with 600 over 4 equals f, which is mathematically okay. So just swapping these, so that force in equals 600 divided by 4. That means that the force input has to be 150 newtons, and I'm putting the unit newtons on because we know that it's a force. So that's the answer to that problem, number 4 there. And you can always check it by actually putting the 150 in here. And sure enough, 600 divided by 150 is 4, so that did work out. And like I said, that is mathematically sound to switch these places if you need to. Alright, our next problem deals with more mechanical advantage stuff. It says you and a friend apply a force of 313 newtons to push a crate up a 2.25 meter ramp onto the bed of a truck that's 1 meter off the ground. The first thing to ask is how much work in joules has been done when you reach the top of the ramp. So we know that work is equal to force times distance. And if we're pushing it up the ramp, the crate itself weighs 313 newtons, so we know we're going to need that much force to push it. And the distance that we're pushing it, since we're pushing it up the ramp, is 2.25 meters. And it's important that our force is in newtons and that our distance is in meters here. And so when we multiply these, in my calculator I'm getting out 700, and 4.25, which looks like I ran out of room over there. And because it's a work, we know the unit is joules. Remember, joules is the same thing as a newton times a meter. So the answer there for A on number 5 is 704.25 joules. In the next problem, it tells us that the work to lift the crate is 490 joules, and then it's asking us for the efficiency. Here we need to remember that the efficiency is the work out divided by the work in times 100, and then we need to put on a percent sign on the very end. So the work out, it already told us, is 490 joules. And the work in, we found out in A, is 704.25 joules. And then we would multiply by 100%, which is just multiplying by 100, and then tacking on a percent sign as our unit. Here, joules are going to go away, so 490 divided by 704.25 times 100, that's like 69.6%. So 69.6% is our answer for part B. And then C says, if it takes you 6.23 seconds to reach the top of the ramp, what is your power output in watts? Remember that power is equal to work over time. So we're looking for the power output, which means we need the work output, which is 490 joules, divided by the time, which is 6.23 seconds. And I know this is getting confusing with all the writing I have here, so I'm going to try to take some of this off. So 490 joules divided by 6.23 seconds. And that's going to be 78.65. I just realized I messed this problem up. This work here should not be 490. It should really be the 740.25 that we had before, because that's how much work we're having to do in order to get it up. So even though this says power output, that's still requiring the work that we needed to put into this process. So 740.25 divided by 6.23, the power is 118.82, and the unit there, joules over seconds, gives us a unit of watts, which is a capital W. So the unit for that answer is watts. And remember, if the work was in kilojoules, and then our unit would have been kilowatts. But in this case, it was just in joules. So the answer there, again, is 118.82, I think, if I did that right. Okay, the next set of problems here says to calculate the gravitational potential energy in the following situations. A is a car with a mass of 1,200 kilograms at the top of a 42.5 meter high hill. Okay, so keep in mind here that the equation we're going to be using for gravitational potential energy is mass times gravity times height. The mass is going to need to be in kilograms. The gravity we know is 9.8 meters per second squared, and the height is going to need to be in meters. So for A, we have a 1,200 kilogram car, so that's going to be 1,200 times gravity, which is 9.8, times the height of 42.5 meters. And remember that that height does have to be in meters. So 42.5 times 9.8 times 1,200. That's going to be 499,800. So 499,800. And the unit for energy is the same as the unit for work, which is joules. So that's our final answer for A, is 499,800 joules. For B, we have a 65 kilogram climber on the top of Mount Everest, which is 8,800 meters high. So we're using the same equation there, which again is mass times gravity times height. This time the mass is 65 kilograms. The gravity is the same at 9.8. And the height this time is 8,800 meters. So then the answer for B that I'm getting, 65 times 9.8 times 8,800, that's going to be, let's see, 560,5600. So that's 5,605,605. and again that's joules. So 5605600 joules. Okay, in our next question here, a student holds a 0.55 kilogram egg out a window just before the student releases the egg. The egg has 8.0 joules of gravitational potential energy with respect to the ground. How far is the student's arm from the ground in meters? So our equation here is gravitational potential energy equaling mass times gravity times height. And this time we're actually going to be looking for the height. We're trying to figure out how high this egg is off the ground. So the gravitational potential energy is 8.0 joules. That's equal to the mass, which is 0.55, times gravity, which is 9.8, and then times the height, which is kind of our question mark or our x. That's the thing that we're solving for. So 0.55 times 9.8, that's 5.39. So on this side is going to be 5.39 times h is equal to 8.0 joules, which means we're going to divide both sides by 5.39, which means that our height is 1.48. And remember, if we're using standard units for everything, which we did in this case, the unit here is going to be meters, because the unit of height is almost always in meters. So for problem number 7, the last problem on this side of the review, it says calculate the kinetic energy in joules, and it gives us this 1,500 kilogram car, and it's moving at different speeds. Remember that kinetic energy is all about the energy of motion, and the equation for kinetic energy is 1/2 times mass times velocity squared. The mass has to be in kilograms, and the velocity needs to be in meters per second in order for this equation to work. So for A, we have 1/2 times 1,500 times 15 squared. So 225, which is 15 squared, times 1,500 divided by 2. The answer for A then is 168,750, and that would be in joules, because we know that energy is usually measured in joules. And for the 25 meters per second, it's the exact same equation, but this time we have 25 squared instead of 15 squared. So that answer is going to be 46,875. 46,875 joules. And the very last one is the same, except for it's 50 squared. So 1/2 times 150 times 50 squared. And actually, I just realized I'm screwing this up. It's not 150, it's 1,500. So this answer is probably wrong. Let's redo that last one there. So 1,500 times 625 divided by 2. Oh, I must have just written it down wrong because, let's see, 468,750. So 468,750 joules was the answer to B. And then the answer to C, where we're taking 1,500 times 50 squared times the 1/2, is going to be 1,800 75000. So 1,875,000 joules for part C. All right, for the law of conservation of energy, like I said earlier on in the video, remember that energy cannot be created nor destroyed, but it can be transformed from one type of energy to another type of energy, and it can be transferred from one object to another. So that's the law of conservation of energy. The next question on here says, explain how the conservation of energy is in operation for a stone you throw off a railroad trestle. Be able to do the same for another example. Remember that whatever energy is inside of that stone is called potential energy, because potential energy is the energy that's stored or the energy due to position. And then when that stone is thrown, that potential energy changes into kinetic energy, because now the stone is moving. So when the stone stops moving, all of the kinetic energy will transfer to the objects that it comes into contact with, whether that's the ground or water or whatever else. The next question asks to give examples of transfer from energy from one form to another besides gravitational potential energy to kinetic energy. One example of this is the fact that cars have chemical potential energy in the form of gasoline, and as that gasoline is combusted, which we'll talk about second semester in physical science, that's transformed into kinetic energy, which is how the car can move and actually drives on the road. So that's one example. Another example is elastic potential energy that's stored within the rubber band, and the kinetic energy from your hands that's transformed into thermal energy by rubbing your hands together. All right, in this next problem, number 25, we're given a lot of different things, and it's asking us to tell us what kind of energy is there. So a frisbee flying through the air, that's going to be kinetic energy because we have motion or movement going on, and that's really our key for kinetic energy. A hot cup of soup, that's thermal energy because heat is considered like thermal energy. A wound clock spring, the spring has potential energy inside of it, so that's potential energy for this one. Sunlight is again thermal energy or heat. A rock that's sitting on the table or on top of a hill, that's gravitational potential energy. Remember, the higher you go off the ground, the more gravitational potential energy you're going to have. And then gasoline in a lawnmower, that's chemical energy, kind of like the example that we just did a second ago. Keep in mind that we can't ever have 100% efficiency because we have loss of heat or energy due to friction. So in a skateboard park animation, the skateboarder going back and forth is losing energy in real life due to the friction of the wheels against the ground. But in a simulation where there is no friction, it would go back and forth forever. Okay, here's a roller coaster, and it's showing us 4 different letters. So there's a blow up of that roller coaster. We have W on top here. X is right there, Y is right there, and Z is right there. And the first question says, list the points in order from the point where the car would have the greatest potential energy, where it's going to have the least potential energy. The greatest potential energy is going to be as high as you can go, so that's W. And then the next highest point is Y, so that's the next amount of potential energy, that's the most. And the next highest point is Z, and the lowest point, in other words, the point where it has the least potential energy is going to be X. So in order of going from most potential energy to least potential energy, it's W, Y, Z, X. And then as far as kinetic energy goes in part B, remember this all deals with motion. So we want the place where it's going to have the least kinetic energy is where it stopped, which is W. So I'm going to make that my last one. The place that it's going to have the most potential energy is going to be X at the bottom of that hill. And then Y at the top of this hill is going to have less potential energy because it's slowing down. And Z is going to have more potential energy than Y. So this is an order from greatest kinetic energy. I'm sorry if I said potential energy, I meant kinetic energy. So greatest kinetic energy to least kinetic energy. The most kinetic energy is at the bottom of that big hill, and the next amount is Z, and then Y has a lot less kinetic energy because it's at the top of the hill, so we're slowing down and moving less. And W, where it's stopped at the very, very top of the hill, has the least amount of kinetic energy. So again, this is most kinetic energy, and this is least kinetic energy.